For the next several examples, we're going to practice the integration method called U-Substitution, probably one of the most useful methods that you will learn in all of your techniques of integration. When you're doing U-Substitution, this is basically undoing the chain rule from derivatives. And if you remember, the chain rule came from having nested functions. So your first step in doing a U-Substitution problem is to figure out what your U is going to be. U often is the innermost function. In this case, it looks like our innermost function will be inside our square root, so we're going to let U be equal to 2x cubed minus 7. After you pick a choice for U that makes sense, the second thing that you want to do is you want to find the derivative of U, or du. So when we take the derivative of both sides of U equals 2x cubed minus 7, we get 6x squared and then dx. Okay. After you pick your U and then you find your derivative of U or du, then the second thing to do is to rewrite your integral only in terms of U's. Now, parts of this integral are easy to write. So when we go to rewrite this integral, it's easy to see this right here. That is the square root of U. So when we have our integral, we'll have the square root of U. And then for the rest of the integral, we have an x squared and we have a dx. Well, for our du, we have 6x squared dx, so we have a portion of our du contained here. What we need to worry about is this extra 6 that we have as a constant coefficient in front. Dealing with extra constant coefficients for du isn't difficult. If we want there to be a 6, so we have 6x squared times dx to be our du, we can easily compensate for that by dividing by 6 on the outside of our integral. So our 1/6 stays on the outside of our integral to make up for multiplying by the extra 6. And then, let me highlight this in yellow, the 6x squared dx, 6x squared dx is only equal to du. So we have times du. Once we've written our integral with only u's and constants, we can usually integrate. In this case, we've got our 1/6. It's nice to change that square root u to the 1/2 power to make the integration easier. So when we integrate, we have 1/6 times u to the 3/2 power. And dividing by 3/2 is the same thing as multiplying by 2/3. And we can't forget our plus c. Okay, reducing our fraction. This is a 3. We have 1/9 u to the 3/2 power. And the very, very last thing to do is to go all the way back to x's. So remember, u was equal to 2x cubed minus 7. So we have 1/9 times u, or in other words, 2x cubed minus 7 to the 3/2 power plus c. Let's continue and do a couple more examples. Okay, next example. Let's take the integral of sine of 5x divided by cosine to the 7th of 5x dx. Okay, remember, first thing to do is to look for your innermost function, your inside function. In this case, it looks like we have something to the 7th power in the denominator, so we're going to let u be cosine of 5x. Then we find our du. The derivative of cosine of 5x is negative sine of 5x, and then by the chain rule, times 5, and times dx. Okay, so when we're rewriting our integral in terms of u's, we've got cosine 5x is our u. So in the denominator, cosine to the 7th of 5x is u to the 7th power. In the numerator, we're close to having our du. We have sine of 5x and dx, sine of 5x and dx. But just like in the previous problem, we're missing some things. We're missing the negative sign and the 5. So if we want to include a negative and a 5, so that now there in green and in yellow we have our entire du, we're going to have to make up for that by multiplying by a 1 over negative 5. So the negative 1/5 that we write on the outside compensates for the negative 5 on the inside. And the point of that is now in the top we have negative 5 sine of 5x dx, negative 5 sine of 5x dx. Now we have our entire du. Everything went out of the numerator, so we're going to put a 1 in the numerator. Now we should have something that we can integrate. So let's try to integrate this. We've got negative 1/5 times the integral. I'm going to rewrite this as u to the negative 7 du. Let's separate these a little bit. Let's see, that's negative 1/5 times u to the negative 6 divided by negative 6 plus c. And when we clean this up a little bit more, we've got positive, let's write this as 1 over 30 u to the 6th plus c. And the very last thing to do is always to go back to x's, so we have 1 over 30 cosine to the 6th of 5x plus c. Finished. I'd like to point out in this problem another way to figure out what your choice of u is going to be, because truly when these problems get any more difficult, figuring out what u is probably the most difficult step. And you're going to experience lots of times where you try a u and it doesn't work. So in this problem, one way to see what u is going to be is to look at the rest of your problem and look for a derivative that you know, like a sine, a cosine, a tangent times secant, or a secant squared. Another way to figure out what u is going to be is to just try. The worst that'll happen is that you'll try wrong. So if you chose, for example, I'm going to make a different colored pen here. This is going to be incorrect. So we'll choose an ugly brown for our incorrect guess. If we had picked u is equal to cosine to the 7th of 5x, we can see that this is an incorrect choice for u when we start to look for our du. Now our du in this case, remember that we've got several chain rules here, would be 6, whoops, I'm sorry, no, would be 7 cosine to the 6th, 5x, and then from the chain rule, times negative sine 5x, and then times one more chain rule times 5. Now here's how I can tell that's not going to work. When I tried to substitute back in everything to be u's, I don't have enough for our du. I don't mind about having a 7, because I could have multiplied by 1/7. I don't mind having an extra 5, again, because I could multiply by 1/5. I don't mind having the sine of 5x, because we have that in the numerator. But what I do mind is the cosine to the 6th power. We already are using up all of our cosine to the 7th powers from the denominator to be our u's. We don't have 6 extra cosines to give away. so that you can tell kind of quickly that this is not going to help. Okay, let's look at one more problem of substitutions. So let's look at, get out of that brown, let's choose a nice blue, the integral of e to the tangent x times secant squared x dx. Okay, picking u. Like I said before, we want to look for the innermost function, but we also want to help ourselves choose u correctly by looking at known derivatives. That secant squared should be recognizable as a derivative that you already know, specifically the derivative of tangent. So if the secant squared is the derivative, this is probably going to be our du, which means u will be equal to tangent x. Du is equal to secant squared, whoops, forgot my c, secant squared x dx. And now let's make sure we can rewrite our integral only in terms of u's and possibly constants. E to the tangent x is easy enough. That's just going to be e to the u. And then secant squared x dx, well, that's nice. That's just our du. So we have du here. Great. We were able to write our entire integral with just u's and some constants. So let's integrate. Antiderivative of e to the u. Oh, I love e to the u. Just e to the u. Don't forget the plus c. And then the last step to do, go all the way back to x's. Since u was tangent of x, this integral is e to the tangent x plus c. Finished.